Good afternoon, everybody. I'm going to talk about feeds and speeds, very deep subject in CNC machining, and also with the advent of the new tricordial style roughing techniques like Mastercam dynamic milling and Fusion 360 adaptive clearing. It's kind of opened up a whole ball game of roughing toolpaths, basically. I came from the older, even hand programming days of traditional machining, and on the right hand side, this is from a Haas video, avoid chatter on your mill. And on the right would be a typical pocket, and how we used to start from the middle and step over until we get to the outside boundary. Except in the corners and this little neck area, it becomes a little difficult. It becomes like slotting, and you're getting a lot of engagement on the radius. On the left is a dynamic or tricordial adaptive style toolpath, which actually keeps on climb. Everything's in the climb milling direction, and it tries to keep the radial engagement at a certain level. Some people will call it a chip thinning formula. Some people have a setting with where it's the step over the optimal load, or any kind of settings they use to control that. But it requires a lot of math, and you end up with a lot of G code. But in some machines, they have to be able to navigate it, because if you get some older machines, they may not be able to do the code as efficiently as a newer machine, process the code. All right, so also I have, what's some other things I have here? So I'm not promoting any particular end mill brand. They all make pretty good end mills. AccuPro, Helical, Kennametal, Zombie Mill, all that stuff. So this is from our supplier, AccuPro. And I saw this HS series, so I had to do some homework when we get into milling steels. So we took some projects like Titan projects, and we converted to steel cutting, and we also did some even pre-programming for other metals, even though we may not have that metal. And what kind of tools do we use? So we have to make a little bit of adjustment on tools. So the face mill that we use in our shop, the insert is capable of cutting different metals. So we leave that alone. And the end mills, we've decided to go to a 4 or 5 flute variable helix end mill. That's the style of end mill that's used for the high speed or high efficiency machining processes. A couple of things you really need is the tool is trying to yank itself out. We're trying to cut at full depth, so you got to have a lot of grip. You can use a side lock, really a standard holder. If the end mill has flats on it, that's effective. The typical ER collet, if it's not torqued correctly, may not work. The end mill still may pull out. They make some milling cutters that actually have a lot more clamping force. Like in our case, we're using a Lindex SK16 collet system. And they recommend torque wrench, so we have a torque wrench for that. We also bought some better caps for our ER32 system. We're torquing those also, and then we've been really successful with those. And you can see some videos on really high speed, like running 100 to 200 inches a minute in your steels. So we took some data here, and we decided we actually experimented with some, but we wanted to get the right tools. Right, we got this HS series, and my thought was 3 flute tools are usually your aluminum tools. A lot of space. It could be uncoated or a coating that's agreeable with aluminum. But the more strength you have, that makes the core stronger. 4, 5, and even 7 flutes are actually pretty effective. But how do you get them to rough? Like this is a 7 fluter here. And this one actually has variable sizes. It says the 38-degree helix with variable index. That's a key part of this component. You can start reading up on why and all that kind of stuff. This has a particular coating for hardness, capable of helical interpolation and ramping up to 5 degrees, suitable for high-speed machining and tricordial toolpaths. So here's your sizes. And you get your typical ball end mill, a corner radius or bull end mill, ones with necks on them, they're reduced. We used to have to make these. You go to our grinder and grind a neck on there. This one's for chip breaking with little notches in it. And your typical finishing flat bottom end mill. So at the very bottom of this catalog, you should be up to date on your feeds and speeds. Now typically we're using a standard feed and speed chart, but we actually learned a lot on this, because if we use the 4 flute version and we decided to go like Titan 1M, which we're using a 3/8 end mill, and if we're doing carbon steel right here, 1018 carbon steel, and we're going to actually, are we going to be full slotting 30% radial, 10% or 5%? So we actually, on the left here is surface feet per minute. So we're actually, this range is a little bit expanded than normal. And you can get the reasons why later on. But right over here, they actually gave you hard RPMs. Usually we're calculating. But so we'll probably go with 30% or less on the radial. But they say this looks like it can do it. So, and if you have a low horsepower machine, the less radial cut will actually still work. So if you did 10% radial, and that'd probably be pretty safe. And then they have some recommendations. Axial depth of cut is how deep we're going. So in this case, if we're 30%, we can go 1.25 deep as diameter. So if we were 3/8 deep, we could go 3/8 diameter, we can go 1/2 inch deep. So in this case, 1.5 diameter would be probably a safer bet. We can go 10 or 15% on the radial or the optimal load in Fusion 360. And radial depth of cut is really 10% of the diameter. That's what they're implying. So in this case, we would run this RPM right there, 3,496 at 40 inches a minute for steel. And then you get into your other metals. You got alloys with the 4000 series, tool steels that are not hardened, cast irons, stainlesses, very difficult metals to machine. These are 2 stainless series. Then you get into your high temp nickel alloy stuff, Inconel, Hastelloy, Waspaloy, cobalt chrome. I have a cobalt chrome knee, so it's part cobalt chrome and part titanium. And titanium, so actually the high temp alloys are like the slowest RPM of all these. So if you look at the SFM numbers, that relates directly to RPM. So chip per tooth is how much each tooth can cut, and that's just always in thousands, small numbers. Surface feet per minute is how you calculate RPM. So if your tool manufacturer says, I want you to run it at 200 to 400 surface feet per minute, that's your range. And you do a simple calculation to create RPM. And in a milling machine, you got to have RPM, revolutions per minute, and it has to feed in inches per minute. So it is a terminology, and you even have the formula right here. RPM equals 3.82 times the surface feet per minute divided by diameter. So that's actually how it's calculated. Now, if you're in Fusion, it's self-calculating. So all these CAD/CAM systems do that, and I could do the same. I'll pull up a Mastercam one to do the same demo later. So in this one, I actually made my own tool library because I actually plugged in all my feeds that I need according to that chart I use. And I've already made parts with it. So in my tool library, in my cloud, I have Titan building block steel. So these are all been preset with the RPMs needed. So this one, we have tool cutting data down here, face mill steel. And that's 12,073 RPM at 24 inches a minute, which equates to 4 thousandths per tooth. Now our Titan, if you use the 4 flute end mill, I have adaptive 10%. I have it all set up right here. So that would be my selection, which really is they're about 3,500 RPM at 40.5 inches a minute. And it's also going to set my optimal load at 10%. So it'll be like 0.0375 on the sideways cuts. So I'm going to upgrade this one right here. I'm going to save as a new part. 21, oops. steel. And I like to say real machinist cut steel, so. Okay, we're gonna upgrade. Edit. And we're gonna select tools from the new library, steel tools. And here I can even just narrow everything down over here. Face mill, we only have one. Face mill steel. I've already pre-selected the RPMs. And other than that, I'm not going to change anything. Everything is ready to go. All right, I got to go all the way down the list here. I got to go edit. I'm going to go select the 3/8 tool, but I'm going to use the 4 fluter. So I'll do flat end mills. I'm going to use 4 flute. Oh, wrong selection. 4 flute by 3/8. I'm going to click adaptive 10% because that's the style of machining. And that presets all my feeds and speeds and also presets this optimal load number right here. But it's all the same parameters, stock to leave and stuff like that. All right. Now if I even put the eyeball on, let it calculate, we should get an updated one. All right, let's go to, yeah, there it is right there. You notice these cuts are very close together. That's the optimal load setting. All right. So now we're going to go contouring. So then we just got to go update all the tools. Once you've already selected a tool in Fusion, you don't really need to go back to the cloud. You just go to your operation or your basic one. Because now we're actually getting different tools in here. So if I go to operation 1, I got the 3/8 end mill, and I have the old one. I have 4 flute and 3 flute. This is the one I want. And this is going to be my contour. So I'm going to reselect that one and hit OK. And I have 2D pocket. And that one is also the 3/8 tool. So I got to go select, reselect the tool, go to my operation 1, select the 4 fluter, and that's pocket, floor, select. Done. Hit OK. 2D chamfer mill. Let's go to edit, select. This one I'm going to have to go to the steel library, pick the, was it 1/4 inch chamfer mill, I think, and select chamfer, select, OK, edit, and yep. I got to go just select the new one, operation 1. I have 2 competing tools. I have, and I probably should relabel these. I got Chamfer Mill 6000 and Chamfer Mill 53. So this is a case where I need to label this better. I'm going to pick chamfer on this one for the updated feeds and speeds for the 1018 steel. Hit OK. And I have drills. Now the drill, so we're going to use the same chamfering mill. Change the end mill, and we're going to use a different drill and a different tap. The aluminum parts are using a forming tap, or what they call a roll tap. Sometimes we're not successful with using roll taps in steels, so we're going to use a proven formula. We're going to use traditional cutting taps. We're going to use a screw, or what we call a spiral fluted tap, so we'll pull the chips out because they're blind holes, and that requires us to use a different drill size. So I got, let's go reselect the spotting drill, which is the chamfer mill drill. I'm going to go to operation 1, and by default the Fusion tries to pick hole making tools for holes, but we're actually reusing a milling tool, and we're going to pick the lower RPM drill feature for speeds and feeds. And another trick here is, yeah, everything's all set to go, chamfer diameter. Now we're gonna change our drill and tap and change the feeds and speeds for that one. Let's select that one, go to steel tools, we're in hole making, and right here is we're doing a 1032 tap, which requires a 159 drill, not the 177 that we normally use for the forming tap. Let's select that one, hit OK, and then drill and tap, final, edit, select, and steel tools, and we're going to pick the 1032 cut tap. And this has a 250 RPM. And yep, hit OK. That's the correct feeds and speeds. So let me just do a quick simulate here, a regeneration. All right, make sure everything's updated. And we'll do a quick simulation. So feed and speeds are a very deep subject, but you want to take this a little bit at a time. So if you mastered the aluminum parts, now where do we go from here? Let's try various steels. 1018 is actually considered to be a low carbon steel. It's probably one of the softer steels, but definitely different feed and speed. So real men cut steel. Let's renumber the tools. Let's get that done. So we're on operation 1. Going to renumber the tools and put them in order of operation numbers, and it'll line up with our tool list. Yep, that's done. And I'm going to do a quick simulate just to make sure everything still looks good from this point of view. All right, I'm going to turn this new machine simulation off, and I use the comparison view because it's blue is big, red is bad, red is dead, and the green is good. All right, slow it down and hit play. All right, green is good. All right. All right, doing a roughing strategy just like we have before. Not much to see on the outside. Only take smaller cuts sideways. That's pretty much the only difference here. All right, then we have regular for, and then let's slow it down for all the others. So our chamfering left a little red mark there, probably because we're going bigger than the diameter. And I look at the modeled one, so let me just make sure that that is correct, and that would be the first drilling operation. So if I look at it, it actually looks bigger than the diameter. So let's go see if we can do a quick fix here. What's our height? It says 2 chamfer diameter, and then chamfer, it's forcing it to be to a certain number. So I'm going to just shut that off, and I'm going to go to chamfer width. And I found lately that's a better selection. That lines up with the hole size. All right, now we're going to post our code. Now if we're in the new NC program setup, I see one here already, but I think if you press this, says NC code out of date. So actually, hopefully we can repost from this side. Hit post. I'm going to save it in my temporary file in the G code. I'm going to run it in the TM1, and I'm going to put it here under Titan 1M steel. So I have a place to put it. Hit save. Successfully posted, and review the G code. So we did an update to use G0s for our rapid moves, real G0s. I got the STC TM1P machine running, and all the tools are aligned. So we're ready to go cut steel. Same size material, 1018 steel, and we'll get back to you on how we did. Okay, thanks a lot. See you later.